All right, here we're going to do 10.3, the integral test. And so hopefully this video won't be too long. This is a not very long section. So the most basic question we can ask about a series is whether it converges. All right, and so obviously that's what this section is going to be about, deciding if a sequence converges. So right here we have non-decreasing partial sums. We have a corollary of theorem 6, which if you remember or not was the monotonic sequence theorem. All right, and that was in the last section, I believe. And basically that was if it was non-increasing, non-decreasing. Go look that one back up in the other video. And basically a series, right there, sum from n equals 1 to infinity of all a sub n of non-negative terms converges if and only if its partial sums are bounded from above. All right, so basically that's what we need to check on. So let's take a look at some examples here. Actually, as a consequence, if the partial sums are not bounded, then it diverges. So basically this will tell us. Now, in the last one, we were looking at something when we were talking about the nth term test, and that could tell us if it diverged, but it couldn't necessarily tell us that it did converge. Everything that converged would give us a 0 in that test, but just because it was a 0 didn't mean that it actually necessarily converged. Only if it was non-zero, that meant it diverged. So let's take a look at this series here. Sum from n equals 1 to infinity of 1 over n. And that's going to be the 1 plus 1/2 plus 1/3 plus 1/4. And if we look at the nth term test, right, where we did the limit as n goes to infinity of 1 over n, that equals 0. And so that's inconclusive. That means it might converge, it might diverge. So we don't know. So let's try, let's show any partial sum. Let's see if it's not bounded or not. So let's take a look at this. We have 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8 plus ... And so take a look at this. I'm going to look at this 1/3 plus 1/4. If we look at that, if we make them the same, this is essentially what? This is 4/12 plus 3/12. And that's going to end up giving you, it's going to end up giving you 7/12, which is greater than 1/2. And if we come over here and look at this part right here, and I'm not going to write that whole sum out too, but if you look at the sum of all of these things, they are also going to be greater than 1/2, which means that we're always increasing by at least, so like we're always increasing by at least 1/2, right? You can keep going and you're always going to be able to add something, add a few terms up that's going to give you something more than 1/2. Therefore, our sum, our sum of 1 over n is not bounded, right? And therefore, it diverges. Okay? Just as simple as doing something like that. All right? Let's take a look at the next one. Okay. Does the following series converge? So, again, if we look at the nth term test, we can do limit as n goes to infinity of 1 over n squared, right? But this equals 0, and so it's inconclusive. We don't know if that tells us it converges or diverges. So let's try taking a look at this. We're going to let our sum of n equal 1 plus 1/4 plus 1/9 plus 1/16 plus 1 over n squared. Okay? And then we're going to let f of x equal 1 over x squared, because we have a 1 over n squared. And so the sum Sn is also going to equal f of 1, that's the 1 over 1, that's the 1, plus f of 2, plus f of 3, plus f of 4, plus f of n. Sorry, I'm going over onto the picture there. But f of 1 would be 1, f of 2 would be 1 over 2 squared, that's the 1/4, 1 over 3 squared, that's the 1/9, so on and so forth. And if we look at that, that is all of these rectangles that are underneath the curve of 1 over x squared, if you look in this picture. And if you notice, the area underneath that curve from 1 out to infinity, so let's write it this way. I don't want to put an equal sign. Let's write f of 1 plus integral from 1 to n of 1 over x squared dx. And if we compare these two things together, f of 1 is just our first term, but if we look at the integral, let's say we look from here where it equals 1 out this way, you'll notice then that there's all these little extra areas in here, right? These little areas where we're going to get more area underneath the integral, the continuous integral, than the total area of the rectangles. If we just look at the rectangles, it's going to be less than the area underneath that curve. And so we have the same f of 1 part, so that part, these part are equal, but this integral here is greater than the rest of the terms. So this whole part right here is going to be greater than what we had on the previous line. And we can then take this out to infinity and make this f of 1 plus integral 1 to infinity, right? Go as n goes to infinity, 1 over x squared. And that's also going to be greater than if we just let n go to infinity as well, because those rectangles are always going to have a little less area than underneath the curve. And so if we calculate this, f of 1 is just 1, plus here the integral of 1 over x squared dx. If you don't remember or not, from last chapter, we had integral 1 over x to the p dx, and it equaled infinity if p was less than 1, and it equaled 1 over p minus 1 if p was greater than 1. Here p is greater than 1, so it's 1 over 2 minus 1, which is just 1. And this equals 2. All right, and if that is the case, therefore, the partial sums are bounded from above, because they're always underneath that. They're always less than that. And so again, therefore, the series converges. All right? And it's going to be actually converges to some value less than 2. Okay? It's going to converge to some value that's going to be less than 2. So let's take a look here, and let's look at the integral test. Basically, the integral test says, let the set of a sub n's be a sequence of positive terms. Suppose that a sub n is equals to some function with n basically plugged in it, f of n, where f is a continuous, positive, decreasing, I know you have to be very specific here, so it's a continuous, positive, decreasing function of x for all x greater than or equal to n. All right, n being a positive integer. Then the series from the sum of from n equals 1 to infinity of a sub n and the integral from n to infinity of f of x dx either both converge or both diverge. Okay? Be careful though. This is not saying, right? This is not saying, all right? It's not saying that these equal each other. This is only saying that they either both converge or both diverge. So this is a not equal sign, all right? Be careful of that. Be very careful of that, okay? If you want a quick example, sum from n equals 1 to infinity of 1 over n squared, it, right, if we look at that, it does not equal the integral from 1 to infinity of 1 over x squared dx, which just equals 1. Okay, so those are not, they're not equivalent. They either just both converge or both diverge. All right, let's take a look at the p-series here. The series in examples 1 and 2 are both examples of these p-series where it's 1 over n to the p. All right, recall that back in section 8.8, that was the last chapter we did, we learned about the integral from that, which I just showed on the previous page. Where is that? I'm just going to copy it real quick. I showed right here. Copy. Oops. Copy. We showed this, right? We had this from before. And so, oops, why is it going back to that? Therefore, by the integral test, a p-series will converge. So it converges if p is greater than 1. And it diverges otherwise. So that's a nice little result to make sure that you remember. So let's do some examples of that. So let's determine the convergence or divergence of this series. All right, so let's take a look at this. Let's let f of x equal 1 over x squared plus 1. And then we ask ourselves these questions. Is this continuous? We're starting from 1 to infinity. So is it continuous on x greater than or equal to 1? And the answer is yes. Is it positive on x greater than or equal to 1? Yes. Is it decreasing on x greater than or equal to 1? And the answer is again yes. So that means that if this integral either converges or diverges, then so will our series. So let's check. Integral 1 to infinity of 1 over x squared plus 1 dx, which you should be able to do at this point and get that it is the arctangent of x from 1 to infinity, which we can make the limit as b goes to infinity of the arctangent of x from 1 to b. And so then that gives us, ultimately, going to give us pi over 2 minus pi over 4 when we take that limit. And that's going to just equal pi over 4. Therefore, our series 1 over n squared plus 1 converges by the integral test. Okay? well, actually, I think I probably could have written that little part a little better. Plus 1. So it's pretty much just that simple as long as that's the case. So let's take a look at this one. And then this will be the last one I do. I'll leave the last one on the next page for you to try. So hang in there. We're almost done. So let's do this. I'm going to write it as n equals 1 to infinity of n over e to the n squared. And so we can get our f of x is going to be x over e to the x squared. It is continuous from 1. It is continuous, it is positive, it is decreasing on x greater than or equal to 1. And so we can check the integral for it. Integral from 1 to infinity of x over e to the x squared dx is going to equal, we're going to do u equals x squared du equals 2x dx. All right, and we have to plug in 1, so u of 1 is 1 squared, which is 1. And so our integral becomes, we end up with a 1/2 out in front, right? Because dx equals 1/2, 1 over 2x dx, like that. The x's will cancel, and we're left with 1 over e to the u du, which is 1/2 integral, oh, I forgot to put this 1 to infinity still. 1 to infinity of e to the negative u du. And we can make this the limit as b goes to infinity of negative 1/2 e to the negative u, 1 to b. And then it's the limit as b goes to infinity of negative 1/2 e to the negative b plus 1/2 e to the negative 1. And that gives us a 0 for the first term and a 1 over 2 to the 2 times e for the second term. And therefore, since this is actually converging to something, right? This is, therefore, our sum in e, our series, is negative n squared converges. All right, so all in all, not a bad section right there, and hopefully it made sense to you. Be sure to watch through it again, any parts that you need. If I went too fast, just rewind it, pause it, think about it as I go through it, and I'll see you in the next class where we can talk about any of this that you might need to. All right, take care.